Hello, I'm Dave and welcome to the City of the Future and the fourth and final video in my series where I restore a Sinclair C5. Now the C5 was marketed as an electric vehicle, so time to see just what makes it tick. I'll take you on a tour of the vehicle electrics, we'll service the motor and fit a safety wiring loom, and make some modifications to the pod which should hopefully make it more reliable. Okay, so I'd like to introduce you to my Sinclair C5 simulator. It's all the electrical components of the C5 laid out onto a board, complete with an original wiring loom. Okay, so we'll just go around quickly to identify the various parts. First up, we've got the control box with its lid removed. This normally lives in the rear of the C5. Then we've got a box here which I've added two buttons, one to activate the motor, and another to activate the horn. We've got a switch to the lights, a thermal switch which I'll come on to in a minute, and the motor, and it's a 12 volt DC motor which has got a little plastic gearbox on there, and it's directly driving one of the wheels just as on the C5. We've got a couple of lamps front and back and a buzzer for the horn, and the all-important pod which contains the head-up display. Primarily two indications. We've got over here on the left an indication of the current drawn by the motor, and over on the right an indication of the charge state of the battery. Now I'm not using a battery here for this demonstration, I've just got a bench power supply, nice and easy to vary the voltage and see how much current we're drawing, but it will be a normal lead acid type battery on the C5. And now for some fine detail on how it all works. Well, first up we've got the control box, and we've got connections to the battery, Norton 12 volts. We've got some cables going off to the motor, and on the C5 these would be much thicker wires because we're drawing anything between 20 and 140 amps. And for that reason, to switch it in, we're using an automotive relay with a high current capability. Now next to the relay we see this rather interesting metal plate. Now that's a shunt, it's actually a 1 milliohm resistor, and that's taking a sniff of the current used by the motor in the motor circuit, and we do a couple of things with that. First of all, we condition it with an amplifier, send it off down the wires to our pod, and we can display the motor current in the left hand indicator. Now, should the motor current go too high for too long, that would be a very bad thing. We might melt all of the laminations in the motor and it would be a useless pile of junk. So we've got an op amp and a couple of transistors down here, such that if the motor current is 140 amps or more for more than a few seconds, it will cut off the control voltage to the relay in order to stop the thing going into some sort of horrible meltdown. Now I can simulate this stall condition, 140 amps for more than a few seconds, by removing this red wire, and you can see what happens. The left display flashes to indicate lockout, and the motor is inhibited. We also need to keep an eye on the charge state of the battery, and that's done in the right hand display. If it falls below 10.5 volts, you'll get an alarm, and a short time later the motor will cut out to prevent damage to the battery. Now, as we've already said, temperature is our enemy with the motor. We don't want it to all melt into a horrible heap of goo. So the C5 has got a couple of tricks up its sleeve to monitor the motor temperature. The first of which is this. It's a thermistor, which is a thermal resistor, and that gets jammed up the middle of the motor in order to take a temperature reading, and that plugs in normally to our control box. Now I can't simulate the temperature going up very easily, especially as it's the middle of winter and very cold in my workshop, so instead of a thermistor I fitted a variable resistor to this box so we can simulate what happens when the temperature goes up. And as the temperature increases, we may find this. So we've activated the first stage alarm on the C5, and we've got an audible indication to show us that the temperature is pretty high. Okay, so that gives us some time to take evasive action, park the C5 up in a safe location. Now, should the temperature go to the next level, the motor's going to be cut out just to protect it all from going into meltdown, and let's try and simulate that. And there we can see all the LEDs flashing and the motor is now locked out. Now, there's a bit of a flaw to this design, because should there be a bad connection between the thermistor and the pod, it won't work. So there's a fail-safe in the form of a bimetallic switch mounted on the underside of the motor casing. So should the motor get too hot, the switch will open and cut the power to the relay. I've simulated this with a domestic heating thermostat, and you can see it working here. First, let's get the motor started and rotate the thermostat to open the switch, which cuts the power to the relay and kills the motor. My control box appears to be in good working order, but while the lid's off, it's worth checking a couple of key components. There's a diode across the motor and the relay coil, and it's worth checking those out with a multimeter. So first of all, I'll put that across the diode, which is across the relay coil, and it should conduct in only one direction and show about 0.5 volt, which is the voltage drop, and that one is fine. Now let's do the same on the diode across the motor, and that's not conducting in that direction, and it's also not conducting in the other direction. So that diode looks to have failed, and that's quite a common occurrence with C5s, because when you're pulling them backwards at anything other than a very slow speed, the motor, which is acting as a generator, is creating reverse voltage, and that, if it's too high, will blow up that diode. Now, this C5 will work perfectly well, but without that diode, you're going to receive some bad arcing on those relay contacts, and over time it will wear out. In the worst situation, the arcing will cause the two relay contacts to weld together, and in that situation you've got a runaway C5. It's not a situation you want to be in. Now, the original C5 had a mechanical switch on top of the battery that would enable you to push a button and kill the power. Now, my C5 has got a car battery, and that switch mechanism is long gone. So I'd be in a bit of a pickle if the relay contacts welded together. And for that reason, and for a couple of others I'll explain later, I'll be fitting a safety wiring loom as my next step. Okay, so here's the safety wiring loom, and it comprises a couple of quick release battery terminal connectors, so you can remove your battery for charging nice and easily. No need to resort to a spanner like in my case. We've got a replacement switch, and it's a 3-position switch. We've got off, C5 powered, and C5 and lights powered. We've got a diode and a fairly hefty automotive relay. Now, the idea behind this is that if you get the battery connectors the wrong way around, it'll stop you blowing up your pod and control box. So let's get it fitted. And the first job with the lid of the control box removed is to disconnect 3 cables that lead to the battery compartment. The first one here is this brown cable, and we've got 2 that require a spanner. We're going to have to cut a few cable ties. Remove the light switch bracket, disconnect the wires, and then remove the switch. Snap in the new switch, and now we can extract the cables from the battery compartment through the hole. I've drilled a small hole to fix the relay to the body using a bolt. Connect up the safety wiring loom along with a purple wire for the lights. And poke the other end of the loom into the rear compartment. We no longer need the black wire, so we can tuck that safely out of the way. Then it's a case of connecting the 3 wires to the control box. Tidy up the wiring with a few cable ties. And finally fit the battery. And I've treated myself to a brand new leisure battery from Halfords. It's a 70 amp hour unit that fits the space and is better suited to the job than the car battery that came with my C5 when I bought it. And a quick check that it all works. And it does. So I've now got a convenient way of turning the C5 on and off, as well as quickly connecting the battery and killing the power should I need to in an emergency. Okay, so let's take the motor apart, check out the condition of the commutator and brushes and the gearbox. We'll clean off any old grease and reapply some afresh. To remove the gearbox, insert some large matches between the plastic fingers and gearbox cover. Be warned though that if you've got the earlier brown fingers, these are brittle and likely to snap off, so you'll want to avoid this and service only the rear of the motor. Now remove the cover by tapping it gently with a screwdriver and hammer. Pull out the gear assembly to reveal 3 planetary gears, so called as they orbit the central gear as they rotate. The outer pinion on which the drive belt sits looks okay. This can be prone to wear. Worth pointing out that there are 2 bearings on the motor shaft. Sometimes the M1 can break off. The teeth on the pinion on the main motor shaft look okay. Take note of the rubber gasket though, which we'll have to keep safe. Turning the motor by hand, it moves freely, which is a good sign, so we'll hopefully just need to give it a light clean and lubricate. I've put some marks on the plastic sleeve and motor case to help alignment when I'm putting it back together. Now we need to pull the brushes away from the commutator. They're spring loaded, so will need to be kept retracted using a screwdriver or 2. And remove the 2 long bolts. Then carefully work the motor housing away from the end cap. There should be 2 metal spacers in here. One is flat, the other crinkled, so this motor has been worked on before. And releasing the brushes, we can see they look in good condition. Inspecting the armature, the end bearing turns freely. The commutator, which makes contact with the brushes, is a little blackened but not too bad. We'll soon clean that up. Next, push the armature out of the motor housing. This is quite difficult as the iron armature is attracted to the strong magnet in the motor housing. This is called the stator. Remove the commutator from the sleeve. And I'll start the cleanup using a cloth. There's quite a lot of black muck from the carbon brushes. The old grease is a bit tacky, so time to scrub it all off using white spirit. Turning our attention to the commutator, clean off the old carbon using fine grit, wet and dry paper. And polish off with a cloth and white spirit. I was able to obtain new spacers for the end cap. And in they go, crinkle first. So on to the reassembly. The first step is tricky as the magnetic parts want to stick together. I found a swift and confident plunge was a good technique. Then insert into the end cap. There's a notch that needs lining up. Make sure the brushes are retracted. Slide on the plastic sleeve, aligning the marks we put on earlier. Then the two long bolts. I've put a few drops of oil on all the bearings before reassembly. And fresh lithium based grease is applied to all the gears. And pop them in the gearbox housing. More grease. Not forgetting the rubber gasket. Pop it onto the motor. And tap it on with a rubber mallet until all the fingers are heard to click into place. And a quick check, the pinion turns freely in both directions. And there we have it, a fully serviced motor ready to go back on the C5. I'd like to thank Paul Grice for his excellent video tutorials, and I've put links to these down below. Paul is currently restoring a DeLorean and his channel is well worth a look. As we saw earlier on, the pod is a key component in the C5 electrics. Now there's not a great deal inside here, but there is a ULA, which is a microchip with some analog and digital electronics. But this is rather susceptible to being damaged by voltage spikes on its input lines. Luckily, there's a few simple modifications we can make to try and make this a bit more robust and hopefully last well into the future. And the mods are detailed in the Unofficial service manual. And as static is our enemy, I'm using an ESD wrist strap. Now, if you remember from an earlier video, I was having connection problems at the pod, and the culprit was this connector here, and it's quite common for these pins to become tarnished. So first of all, I'm going to give them a good clean with a fiberglass pencil. You could also use some very fine grit, wet and dry. And here's the Ferranti ULA, or Uncommitted Logic Array. It's an early type of custom chip, and similar devices were found in Spectrum computers and BBC Micros amongst others. It's worthwhile removing the ULA in order to clean its contacts, because these too will have been tarnished over many years. Now, although I'll be using a chip puller, you can find that chips are well and truly stuck into their carriers. So I'm going to gently prise the chip upwards a little tiny amount using a screwdriver, just to make it a bit easier to extract. And then use the chip puller. And now I can give those legs a good clean with my fiberglass pencil. There's 4 electrolytic capacitors on this board, and I know some people like to replace them en masse, but they're not known for failing on the C5 in either the control box or the pod. There's no signs of leakage, and I've measured them with my ESR meter and they're good to go, so I'm not going to replace them. And now for the reliability modifications. The first one is to cut the track to IC pin 3 and insert a 47K resistor from this pin to connect to pin 6. And finally, add protection to ULA pins 1 and 4 using diodes. Now this was a bit fiddly, so I've not filmed it, but you can see the result here. Now these diodes act as catch diodes, spiriting away unwanted high voltage signals to the power rails. Normally a signal on our input line is low voltage and neither of the two diodes conduct, and the signal carries on to the IC as normal. Should a spurious high voltage signal appear on our input line, the diode will conduct. So let's say we've got 10 volts on the input line, the top diode will conduct away that voltage to the 5 volt rail. If we had a negative going signal, for example minus 10 volts, the lower diode would conduct and spirit away that unwanted signal to the 0 volt rail. I've gently cleaned the board using a toothbrush and some alcohol to remove any flux, and then carefully refit the ULA, taking care to line up the notch on the chip with the notch on the board. And that's it. We just need to reassemble the pod and then slot it back into position on the C5. Well, that's the C5 all finished, and I'm really pleased with the result. It was in reasonable condition before I started, but it was challenge enough for a mechanical novice such as myself. So, time to take it out for a ride around Milton Keynes. Now, here in the city of the future, we've got a grid system of 60-mile-an-hour roads linked by over 140 roundabouts. It's no place for a Sinclair C5. But luckily, where we're going, we don't need roads because we've got the redways. Bye for now.